Alright, so thanks for the introduction and thanks for the opportunity for me to present our paper here at this workshop. So I'll be talking about joint work with Bart Jacobs, who is already left, went back home. So I'll be talking about coreflections in algebraic quantum logic, and I suppose I should probably make it more precise what I'm talking about. So I'm going to show this slide here. So here we have a sequence of categories. And most of these things have been studied as some kind of quantum logic, so I should probably explain what the abbreviations are. So on the left here we have Boolean algebras, which are not very quantum, which is really classical logic. And we have orthomodular lattices, with the prime example being, of course, the closed subspaces of a Hilbert space. And they were probably the first thing that was actually suggested as something which could be called a quantum logic. But it was not very satisfactory because there is no proper tensor product in these things, and we would like to have some tensor products in quantum mechanics. So they generalized this, and we had orthomodular posets, orthoalgebras, and vector algebras. And so we put the next one at the end here, which is called PCM, and stands for partial commutative monoid. This is not really any kind of quantum logic, but these last three things here, they all involve some kind of partial operation, so we thought it was a good idea to just study that partial operation by itself as its own structure. And we think it's worth studying. So a lot of people have actually looked at these objects over like several decades, and they've done lots of stuff with this. But there's never actually some very categorical treatment. So what we did in this paper is we take a look at all these categories, these inclusion functors, from a categorical perspective, and so we ask some categorical questions about the diagram here. So the first question is here, we have some set of functors. So the obvious question is, do they have adjoints? The answer is yes, all these functors have left adjoints. So in this talk I will not actually go into the construction of these adjoints, and it's also not in the version of the paper that's in the proceedings, but it will be in the later version. The next question is more related to the structure of the category. So what kind of categorical structure do these categories have? Quite a lot actually. So they are complete and co-complete. So for these two it's obvious because they're just the usual algebra stuff, but for these it's somewhat less obvious. And then also there's some symmetric monoidal structure on these categories here, the tensor product if you will, which is obviously what we want in a kind of quantum setting. The way we've gotten these results is using the types that are coreflections. So these partial operations on these four categories, they are a bit tricky to work with. So we have to figure out some trick to do that, and the trick we use is our coreflections, which I'll explain in a bit. So I'll start by explaining what a PCM and a vector algebra is. And I will not actually go into these categories here for this talk because I only have limited time. And it's actually just a special case of the more general one. So what is a partial commutative monoid? So we need some kind of set M, some unit element M, and some partial operation which are written here as a circle join. You shouldn't think of it as a join, it just can be a plus or a sum, some things. We just use this symbol because the circle plus symbol we like to reserve that for monoidal structure on categories. So that's why. So we want some axioms to say that this is actually commutative monoid except with a partial operation instead of a total operation. For this we need this notation here. We say x is orthogonal to y, this sum is actually defined. And then we have three axioms, and I'm just going to put an example here as well. And these axioms are basically basically the commutative monoid axioms except for partial operations. So the first one says you should be able to add 0 to anything and not change it. The second one is basically we want to say we have commutativity, but we need to take into account that it's partial. So basically what it says is if this side is defined, then this side also has to be defined and they must be equal. And the same for the associativity, which is a bit longer, but basically what it says is if you can write this down and this is properly defined, and what on the other side is, it should also be defined and they should be equal. And together with the commutativity axiom, this also implies the other way around. So basically you can read all these three equations in a way, if one side is defined and the other should also be defined, they should be equal. So these are direct generalizations of the commutative monoid laws. So here we have a very canonical example in some way, which is the interval of real numbers between 0 and 1. We can add these together, but sometimes if you add two of these together, you get something that's bigger than 1. So we have to restrict the definition of this point to actually account this is only a partially defined operator. So basically what we say, if this left side is defined, the right side should also be defined and it should be equal. And so we get a category which we also write with PCMs and boldface to indicate that it's a category. So now we move on to effect algebras. So effect algebra is a PCM with some additional structure which is written like this with the perp symbol, which is usually called an ortho supplement. It should be a unary operation, but it should be total instead of the binary one, which is partial. And we need two additional axioms, so this perp is a unique element. This unique is really a key property. As you can add to x and then you get 1, which is defined to be the perp of 0. And the second axiom is 1 should be like the biggest element. You can't add anything to 1 because then you'll go outside of the scope of the effect algebra. We also need homomorphisms, which are just PCM homomorphisms, but we have some additional structure here, this 1, so we should also preserve that. And it automatically implies that this perp is also preserved. And we get a category, which is a subcategory of PCM, non-full. So some more examples. So the unit interval I showed you is an example of a partial commutative monoid. It's actually an effect algebra. You just need to define this perp thing. You should just define it as 1 minus x. And the axioms are obviously very obviously satisfied. This is in fact just an example of a really general thing. If we have any partially ordered abelian group, should we say abelian here, with some positive element, and we can form a so-called interval effect algebra, consisting of all the elements that are positive but less than the special element u. And so in this case we just take the group to real numbers with its usual ordering. We take u as 1 and we get it. So these interval effect algebras, they're a strict subclass. Not every effect algebra is one of these examples, but a lot of examples from physics give such interval effect algebras, including the key example, which is where the name effect algebra comes from. It's the effect of a Hilbert space, which are the positive, which I did it, the positive self-adjoint operators, which are less than the identity on the Hilbert space. Another example is the one that gave these functors I showed you in the beginning. Those were not orthomodular lattice. We wanted to define this O-join symbol as the join, but in order to satisfy the axioms, we need to restrict the definition because we can't add anything to 1. And it turns out that the right way to restrict this is to only define this if x is less than the complement of y. I'll need this example later, so try to remember it. I now move on to coreflections because I can't really do a lot with these things. They're hard to work with, as I explained. So what we're going to do is construct a coreflection with these on the one side. So the definition of a coreflection is just an adjunction that where the left adjoint f is a full and faithful functor, and this definition is equivalent to saying that the unit of this adjunction is a natural isomorphism. And these have very nice properties. For example, if we have some junction, some coreflection between A and B, well, f is supposed to be the left adjoint part of the coreflection, then we can transfer all sorts of structure that's on B. We can transfer that structure using this coreflection to A. In particular, this is a very old result, probably folklore, that if B has limits or co-limits, then A is the same co-limits. So basically how this works is if you want to say, for example, commute a co-product of 2 elements of A, you apply f to it, so that you now in category B, which has co-products, so you take the co-products, and then you apply the right adjoint functor, and this will give you a co-product in the category A. So in our paper we extend this. So if we have symmetric monoidal structure here on B, we can use the same trick and transfer this structure to A. For this case we need some conditions, because we want to play this junction, we want it to play nice with the monoidal structure. So it also has to play nice in this original case. Basically we have a monoidal structure here on B, and we go from B to A and back, it should be a monoidal functor. And if this is the case, we can use this monoidal structure in B to define one in A in the exact same way. If you have 2 elements in A, you apply F, and then you take the tensor product and you apply G, and this gives you a monoidal structure on A. And furthermore, we can also do the same for adjunctions. For this we need a bit And the result basically is if this K, this upper thing here, has an adjoint L, can be either a left or a right adjoint, then this lower should also will also have an adjoint, and then adjoint J is just a composition of first doing F2, then doing L, and then doing G1. And this will be a left adjoint if L was a left adjoint, and it will be a right adjoint if L was a right adjoint. So now we have these transference results for coreflections. So the plan is to make some coreflections with these PCMs and the factor algebra so we can use all these results. Yeah, that's basically what I said earlier, they're hard to work with. The trick is to make a coreflection with some total structures. In order to define some structures, we have to also have operations, but these operations will be totally defined. And we know lots of stuff from universal algebra we can apply that to these things. So first, we're going to do this for partial commutative monoids. So we need a target category, which will be a category which we'll write DCM, downsets in commutative monoids. To define this, we need a little factor by monoids. Every monoid comes equipped with a preorder by definition. You automatically have this, where x is less than y. If you can add something to x, you'll get y. So x is like a part of y. And then to define this category, we need objects, and these objects are just commutative monoids with some subset U. And this U should be a non-empty down-closed subset, where it's down-closed with respect to this order on M. And then we also need morphisms, and they're just monohomomorphisms, except that I need to respect this downset. I need to map this downset into this downset over here. Now we need to define functors, which will make up the coreflection, and we'll call this process totalization. And we'll define a totalization functor in the following way. So if we have some partial commutative monoid M, we construct this thing over here. So I should explain the notation. This script M is the free commutative monoid generated by this M. So this consists of all formal sums with integer coefficients and all the elements big. So this, for example, is an example of one of these formal sums. And then we divide out a relation generated by this relation, which basically says if we can already add some things together in our partial commutative monoid, then the sum in this free monoid should be the same thing. And then we get this set here, which is a bit tricky. You can verify this is actually a downset, which is not immediately obvious. And you can also extend this in the obvious way for functors, but it's basically just using this functor here to extend it. So we get a functor in one direction, we need the partialization functor, so back. And the trick here is this U of these objects. It was a downset in a normal commutative monoid. We just take that U. The U is actually, we view that U as a partial commutative monoid embedded into a bigger thing. And so this totalization functor will be some kind of universal way to embed a given partial commutative monoid in commutative monoid. And the neat thing is, this actually turns out to be coreflection, and so we can now actually apply all those results I had about coreflections. We can transfer limits and colimits, we can transfer monoidal structure, we can transfer junctions if we want to. We're going to do the same thing for factor algebras, and we'll need something which we'll call bar commutative monoids, which are commutative monoids with some special element U, which I'll call the unit, with two additional properties. This monoid needs to be positive, and if we add two different things to A, we get this unit, and those two different things actually were the same thing. And so to get homomorphisms, you just take monohomomorphisms that preserve this additional structure. And we can view this as a non-full subcategory of the previous category by taking all the elements below this unit as a downset. And so previously we had monoids with downset, and those downsets will be viewed as PCM sitting inside monoids. In this case, we view all the elements below the unit, we view this as an effect algebra sitting inside a monoid. So these axioms are chosen in such a way that this thing is actually an effect algebra. With defined in the obvious way, the only way really. But there is something strange going on here. So when we do partial commutative monoids, the three axioms were basically just the monoid axioms except written down for partial operations rather than normal total operations. But here's something strange that's going along. The cancellation law actually holds in all effect algebras, but it does not require to hold in these bar commutative monoids. And there's actually a very good reason for this, because every positive cancellative monoid can be embedded into a partially ordered group. But there exist effect algebras that cannot congruences on BCMs, which are just monoid congruences with two additional actions that they actually, if you divide them out, get a BCM again. They're not very interesting, but the nice thing is we can also put these things on regular commutative monoids. And if we divide these out, we get a BCM. But these do form a closure system, so we can make sense to talk about the smallest congruence containing a given relation. And we can use these to construct like limits and colimits. For example, to construct a product of two of these things, just take the Cartesian product, which is very simple. So this is one of the things where those unigroups don't work because they work. You can form a product of unigroups, but it won't be the Cartesian product. It will be something more complicated. And the co-product is similarly very easy. You just take the monoid co-product, except that now we get both u and u prime sitting in there. We only can have one unit, so we just need to divide out something so that this makes these units equal again. The same thing for equalizers and co-equalizers. If you want to take the equalizer, we just do the normal thing of taking a set where they agree. If you want to take the co-equalizer, we also do the normal thing. We just divide out the smallest relation such that they are equal. And so we get the standard category theoretical result that BCM is co-complete and complete. And we can use the coreflection now to show that the effect algebras also have the same structure. Now, some of this we can actually already describe directly in effect algebra. So product, co-products, and equalizers, they're quite easy to describe directly. These co-equalizers, they're very hard to describe directly, and I'll give you a nice example here. So I have pictures of two effect algebras here. These are actually the orthomodular lattices. So this one on the right is just a Boolean algebra with 16 elements. And this one on the left is actually the co-product of two Boolean algebras with 8 elements. And there is a map from here to here, which hence these I'll describe what it does in this atoms. So A, B, C, and D just get mapped to A, B, C, and D. This X get mapped to C plus D. So these things get mapped to there. And A, B, and Y also get mapped to the same thing here. This is easily seen to be isomorphism because the image contains these 4 atoms, and so the image generates the entire thing. This is actually a regular isomorphism. I can find some maps, really simple ones actually. So this map is the co-equalizer of those two things, and this in no way can arrive from dividing out some congruence in this thing, because this thing has 16 elements and this thing only has 14 elements. So I actually have no idea how to describe this in the category effect algebra itself. You really need these total structures to make this easy. Now we also want tensor products. So once again, it's simple. You just take the monoid tensor product, and this may not be a BCM, so just divide out the smallest relation, so it is a BCM again. And of course we get tensor products of effect algebras using the coreflection again, so you just apply the totalization functor to the things you want to tensor, then take the tensor product, and then partialize again. And so we can, I forgot to mention, this coreflection result only transfers symmetric monoidal structure, but these are actually tensor products are more than just any monoidal structure. There is a notion of bimorphism on both this category and the category of effect algebras. And these are actually the tensor product for these bimorphisms. And this is a bit wonderful as this actually happens. What seems to be the case is if we have two bimorphism of effect algebras, we in some sense can totalize that as well. So they don't actually live in the category of effect algebras, but they seem to cooperate very well with this totalization functor, and we can extend them to a bimorphism of bar commutative monoids. So I'm just going to show a final example of compact effect algebras, which are basically what it says on the thing. It's an effect algebra that's also a compact set. So Howard Barnum in his talk last Friday actually drew some pictures on the whiteboard of some examples of these. But we can actually describe them really in a categorical way. So the unit interval 0, 1, we can actually turn this into an internal monoid using the multiplication as a multiplication of the monoid. And a lot of properties that are ascribed to this 0, 1 thing actually all follow from this monoid structure. For example, a state of an effect algebra is a monoid homomorphism into this unit interval. And there is a theorem that the product of two effect algebras that have a state is the tensor product of two effect algebras that both have a state is non-trivial. If automatically non-trivial, this just follows from the monoid structure. This 0, 1 doesn't really play a special role. We can just take any internal monoid and we get the same
to basically solve the tensor product problem in the sense that if you have a Hilbert space effect algebra, say E of H1, and another Hilbert space effect algebra E of H2, by taking the totalization and then the partial, do you get E of H1 tensor H2?
These totalizations of